Okay, welcome back to our discussion on op-amps and circuits based on op-amps. What I'm going to talk about now is an expansion of what we did in the previous video. In previous video, we looked at two basic configurations of op-amps made with a resistive network or maybe multiple resistive networks around them. And we saw that right away that we could do a lot of interesting things with those op-amps, from basic amplification to making a voltage buffer to having a positive or negative gain to adding signals to each other or subtracting them from each other with their own weights. Now, one thing that I want to go back to and mention here is that all of that magic, all of that interesting thing happened because we had this device where we saw that V out here is A times V plus minus V minus, and I in for both of these terminals was 0. Now, interestingly here, what we said is that this A naught approaches infinity. So these two behaviors, these two, we call them the golden rules for the op-amp. The infinite gain, let us assume there is a virtual short between the two inputs and do all sorts of things. Now, in theory, when you look at this, this is not a workable device. A tiniest difference between the two inputs, because of the infinite gain, should throw the output to, in theory, infinity, but in practice, it should be always saturated at positive input or negative input. What tames this device, this wild beast that you see here, is the feedback network that you put around it. You always go and take the output of the op-amp and feed a portion of it back to the input so that the op-amp knows what is going on around it, and by doing that, you tame this behavior, right? You always need to do that. And you always need to do that in a way that the output changes resist the changes at the input. So, or the other way to say that is that the feedback network creates changes at the input of the op-amp to push the output away from those infinite values that it is going to approach otherwise. And I'll show you an example in a second. But whenever we talk about these linear op-amp circuits, you have to have a negative feedback loop around the op-amp. Otherwise, this relationship that we're assuming here is going to make the op-amp unusable for linear applications. So the requirement for negative feedback is a must. Without negative feedback, you cannot really get any of those benefits. How does that work? So let's look at a non-inverting circuit, for example, and I would like you to go and do this for the inverting one and see if you can follow the signal around and make sure that you have negative feedback. So in this case, let's look at what is going on inside the op-amp. Let's assume that V in goes up. If V in goes up, what happens next is that your op-amp, we assume this fellow here has infinite speed. V minus at this point, the voltage at the non-inverting input is 0, right? Before anything happened, let's assume everything is starting from 0. V minus was 0. V in goes up by a fraction of, I don't know, a microvolt or nanovolt, but as soon as that happens, the output voltage will jump up, right? Remember, V out is A times V plus minus V minus. So as long as V minus hasn't changed yet, it is still staying, staying in peace and quiet. V plus changes a tiny bit, V out goes up. And the op-amp responds to this. As soon as V out goes up, the resistive network that you have created here, you have a voltage divider between them. So V minus that is created from that voltage divider goes up. And when V minus goes up, what happens again if you go back and look at this equation here? Now let's assume that V in has gone up and is now stable at this point of time. V minus is now going up. V plus is stable. V minus is going up. V out is pulled back down. right? So now what you see here is that your input signal is pushing V out up. The voltage, the network that you have created around this op-amp will pull the voltage back down. They move in opposite direction. The network will create resistance towards the changes at the input. And this behavior, as long as you do this, then V out value is going to stay bound and it's going to be limited to a range of values that you need in your linear application. So this negative behavior, this negative resistance, this negative feedback, you always need around op-amps. And then you get all those benefits of the golden rules and so on and so forth. And this negative feedback should exist at all frequencies, under all conditions. So even if your op-amp is not seeing the output for a portion of the frequency band, you're going to have problems. In that portion of the frequency band, you're going to have an infinite gain that will put the op-amp out of its linear range. Now, knowing that, let's look at a circuit similar to what we had for an inverting amplifier. Well, if you use phasors, if you assume V in and V out are sinusoidal signals and Z1 and Z2 are two frequency dependent impedances, similar analysis that we did for the resistive case will give you this expression, right? Assuming your op-amp has infinite speed and all that, you get this expression. And therefore, you can actually start to shape the frequency response of your circuit. You can use those two frequency-dependent impedances here, let's say one capacitor and one resistor, or one inductor and one capacitor, all sorts of combinations, and get a frequency-dependent response. Right away, this should tell you that you can make filters, right? You can do analog signal processing. You can play with the frequency response of the circuit or time response of the circuit by this combination. And let's look at two special cases. So case one, let's look at a situation where I have a capacitor for the impedance in the feedback loop and a resistor for the other impedance. If I look at the V out, V in relationship, it's going to be the impedance of the feedback loop over the input resistance, right? Or minus, what I can see is that V out, if I use the, if I stay in the S domain, is minus 1 over RCS V in. Or if you want to put it in J omega, in terms of J omega, you can say that V out J omega is equal to minus 1 over RC times 1 over J omega times V in S. Okay? So that's the input-output relationship. But there's actually more here to tap into, or look at. We need to have a closer look at this relationship. So for those of you that remember this expression from your engineering mathematics, this should remind you of something. You have an output voltage and a signal that is equal to 1 over S times another signal. Forget about the 1 over RC or minus 1 over RC, it's just a constant. But V out is 1 over S times V in. And if you go back to your table of Laplace transforms or recall what you had in engineering math, that means that V out is the integral of V in. when you multiply it by 1 over s, you get the integral of that signal. And then you have a gain value that is minus 1 over RC. Now let's see, okay, so this is if I go, so I have an integrator. Right? So this is from the S domain. Let's see if I can see the same thing in time domain, right? So let's assume that I have V in. I can show that I1 is V in over R, right? We saw that before. There's nothing new here. Because the virtual ground here produces a 0 volt, right? And the 0 current here means that, all of the current that I produce here will go through the capacitor. Now, if you go back to your circuit theory and recall that for a capacitor, the relationship between the current and voltage across a capacitor, right? So let's just call that VC. I is equal to C dVC over dt, right? For a capacitor, that was the basic relationship that defined the behavior of the device. Or if you're interested in VC, you could say VC is equal to 1 over C, the integral of I dt. Okay? So this is how a capacitor works. Normally, you start from some 0 time and then integrate to time t. So this is VCt plus some VC naught at the very beginning of the whole operation. Right? For integration, that's how you should write it. Let's keep it simple for now. Assume VC naught is 0. Now, if I go back and use this expression that I have here in the circuit in the above, I know I1 is V in over R. I know all of I1 is routed through C1. And I know VC is minus V out because, if you look at the notation that I have here, VC, the way I chose it, is equal to be 0 minus V out. So VC is equal to 0 minus V out, or V out is minus VC. Okay? And then I write VC from that relationship in the above. So it is 1 over C minus 1 over C, the integral of 0 to t I1 dt plus VC naught. And then I have an expression for I1 from here. Plug it in here. At the end of the story, I have V out t is equal to, for I1 I put V in over R, bring R out, so it is minus 1 over RC, the integral of V in. Okay? So if you write the equations in time domain, you can actually see the function right in front of your eyes. It is an integrator as the initial guess or intuition told us. And this is very valuable again. As soon as you have an integrator, you have the possibility of doing all sorts of interesting functions. Now you have the possibility of summing up tiny signals over time, looking at the integral of the signal over time, integrate the noise away, make filters, or, as I said before, solve differential equations, which is super interesting in analog computation. Let's look at an example. Now, the only issue is that you have this 1 over RC factor in front of your integral, and this VC naught that may bother you from time to time. But let's just, those two are under your control. So, for example, you can discharge your capacitor at the beginning of the integration operation, so you start with a VC naught of 0, and RC are your choice. You choose the value that you need. You can actually set them even to 1. So you use a, let's say, 100 nanofarad capacitor and a 10 mega ohm resistor, you get a gain of 1. The negative sign, there is nothing you can do about it. It comes from the configuration of the circuit. So let's go and have a look at the example here where I have an integrator. And the question says, what happens if you apply pulse to the input of this circuit? So you had nothing, then a pulse, and then goes back. So this is, let's say, V in with time. Okay? Question is, what happens in a circuit like that? Okay. So what we can do is that, well, as long as there's nothing at the input, if I look at the output, or maybe you can go and write the expressions, but I'm just going to give you a feeling about what happens. So as long as there's nothing at the input and VC naught is 0, the output will stay at 0. When the input pulse comes in, then what you have is from t equal t naught forward, you have a constant value. So let's just say whatever, let's say V naught. Or I'm using the naught thing too much. Let's just say A, right? So you're integrating a constant value. And if you do that, if you go through the integral, while integrating a constant, it gives you AT for the integral here times the 1 over RC value. So what you expect is a ramp, right? So you'll see a ramp between, let's call it T1 and T2. It's the integral of a constant. And then at T2, the input signal goes back to 0. Well, at this point in time, well, the integral goes to 0, but you have a voltage on the capacitor, right? You've charged the capacitor with that current at the input over that, T2 minus T1 period. And the capacitor is going to maintain that charge. So if I give you that input, that's how the output is going to look like. It integrates the input, and then at the end of that period, the voltage will stay the same as what it was before. So that's how a proper integrator should work. And, again, you have your scale factor here, right? So this value is going to be A over RC, or the slope over there. You can actually calculate it. A over RC times T2 minus T1. Okay. So this is, a really nice circuit. It lets us do a lot of interesting things that I mentioned. However, there is a problem with this circuit, and I hope that by inspecting it a bit closely, you should see that. Remember, the problem here is from the fact that we said we always need to have feedback from output to input in order for the op-amp to doesn't behave crazily, right? We need the feedback from the output to input at all times, in all frequencies, for the op-amp to stay well behaving. It doesn't happen here. If you look at this circuit, the output does not see the input or does not affect the input at DC. The capacitor that you have there is an open circuit at DC. So what happens is that in order to maintain the feedback even at DC, what we usually do is that we usually go and put a capacitor here in parallel with this capacitor. The problem is that as soon as you do that, you don't get your nice ideal integrator anymore. So if you go and look at the transfer function for this device, so I'm going to redraw that. Well, you know what the circuit is. The transfer function for so this is my ideal integrator, but if I use that ideal integrator, I do not have feedback at DC, and therefore my op-amp will almost certainly saturate. So what I do is that I go and put a capacitor here in between the two terminals. And what you can do to figure out the input-output relationship is go and find the equivalent impedance for this combination and divide it by R1, and then what you have is this. Actually, this is in S domain. Let's just write it in S domain. Now, what is happening here, sorry, S, there's an S here as well. What is happening here is that by including that RF over there, well, if you look at an ideal integrator, the gain at DC is infinite, open circuit for C, it means infinite gain for DC and therefore trouble. You don't want infinite gain. By putting that RF there at DC, you reduce the gain of the circuit to, the bottom side. This portion will go away, right, with S0. You're back to your basic non-inverting amplifier. You can choose RF to be really, really large so that you maintain a large gain at DC. And then at high frequencies, you want to make sure that, whatever range of frequencies that is of interest to you, wherever you want this circuit to behave like an integrator, you want to make sure that in those frequencies, this becomes larger than this one very, very quickly, right? So let's say if you're interested in processing signals in 1 kilohertz range or audio band is about, let's say, 50 hertz to 20 kilohertz or 100 hertz to 20 kilohertz. You want the circuit to behave as an integrator in that range. You go and choose your RF such that RFCS at that, let's say, 100 hertz is already much larger than 1. And if that's the case, you can ignore this one, and you can show that you go back to your integrator over that frequency range. So there is really not a huge limitation here, unless you're really going to, you need to amplify or integrate really, really slow signals, low frequencies. This is not a bad limitation, too much of a limitation in most practical situations. But you definitely need that RF, otherwise you don't have feedback at DC, and without feedback, the circuit, the op-amp becomes the beast that it is, right? Infinite gain at the output, doesn't see any input-output relationship, so the output will saturate very, very quickly. Another thing that will happen when you put this RF across the C is that at very low frequencies or very slow signals, remember that we had that pulse, for in your example, that we integrated the pulse, you get a ramp going down, and then the voltage across the capacitor stays constant forever. Well, by putting that RF across the C, that will change, right? So now the voltage across the capacitor start to decrease over time. It's going to discharge through the resistor over time. And the question is that, how much time do you have? Is that going to be a problem or not, right? So thinking about these issues in frequency domain and time domain should get you to the same result. So if you want the circuit to maintain that charge for a very, very long time, you want to use a very large resistor so that the leakage current is small. And if your, time responses are faster, you don't really need it that much, you can use a smaller RF. If you look at this Laplace transform, which is that discussion in frequency domain, you can talk about it in the same way. Fast signals, high frequencies, you probably can get away with the smaller RF. Low frequencies, you need to have a larger RF. Okay, so that's one interesting combination for the impedances that I put around the circuit. Let's look at the second case, where I put the capacitor at the input. So I keep the feedback resistor, but I take the capacitor and put it between the input and the inverting input of the amplifier. In this case, what happens is that, again, you go through the Z2 over Z1 calculation. And you can show that Z2 is, in this case, minus R. You have the negative sign. Z1 is 1 over CS. And therefore, if you want a relationship between V out and V in, it's minus RC S V in. And again, if you go back to your engineering math and what you learned about Laplace transform over there, you know that when you multiply a signal by s, it's as if you've taken the derivative of it, right? So this is in frequency domain. In time domain, you should be able to see the same thing. So in here, we have the relationship for the capacitor, I is C dV over dt. We saw that, right? The voltage on the right side, well, there is a virtual short here, and therefore a virtual ground. So the voltage on the right side of the capacitor is 0. The voltage on the left side is V in. So therefore, I is, let's say let's just keep it I. I is C dV in over dt. Now, because the current that goes into the op-amp is 0, all of this current is rerouted through R, and then the voltage across R, so if you take this as the voltage across R, 0 minus V out is the current times the resistance, so it's IR, and then you can write V out in time domain this time to be, or you can show it to be given by this, 1 RC dV in over dt, right? So the same thing that we said about this circuit using the Laplace transform, if you write the equations in time domain, you get the same relationship. It's a differentiator, right? The circuit takes the derivative of the input. Again, it looks like a very interesting block until you saw a couple of practical limitations. So this is a differentiator. Let's go through one example. And one good quick note, we don't really have to worry about feedback in this case anymore, right? The feedback at DC exists. The R in the feedback loop is providing the feedback at DC and all other frequencies. So we really don't have to worry about the stability of the circuit, but we need to worry about its response, as we'll show you in a second. So the question is, what happens if we apply the same pulse to this input? So V in time and then the question is what happens to V out. Okay. So before T1, the input is 0, the derivative of 0 is 0, everything is going to stay at 0. So 0 at the input, 0 at the output. I expect a 0 volt at the output. Once that pulse comes, it's by definition an instant change, going from 0 to some value at 0 delta t. Mathematically, I should get an impulse if I get the derivative of that. Okay? But I have a negative sign, so the impulse will be pointing downwards. After that, between T1 and T2, the value of the input is constant, so the derivative of a constant is 0, all the way to T2. And at T2, I get a negative slope, but my circuit has a negative gain, so I get a positive impulse here, and then again 0 at the output. So the signal that came in, I took the derivative of it. In practice, I don't have an impulse, right? I don't get an impulse. Impulse means that the amplitude is infinite in in 0 delta t, 0 width, right? So what happens is that you get these really sharp peaks, how sharp they are and how high the output voltage is, depends usually on how good your op-amp and how fast your op-amp is. But you will see something that looks like a spike. Now, here is the problem. What an integrator did is that it amplified the low frequency signals. Remember that if you go and plot the input-output relationship for an amplifier, for an integrator, so this is V out S over V in S, right, the transfer function, and if this is, let's say J omega, and if is j omega, this is your transfer function, right? So it's 1 over s. Right? And remember, this is not 0. You know, j omega, this is usually, this is a logarithmic. For both x and y. So this is log of this, right? This is also logarithmic. If I plot this on logarithmic scale, I will have a straight line. So this is 1 over s. That's the 1 over s behavior. And the gain increased as I went to lower and lower frequencies. For a differentiator, you have the opposite case, right? So for a differentiator, if you look at the V out, V in, and j omega, this is your transfer function. So this is s, right? So your gain increases with frequency. Why do I have a problem here? Well, the problem I have is that a lot of the noise in typical applications appears as spikes. So if your input, your true input is something like this, your ideal input is something like this, or ideal signal is like this, practically you get some noise on top of this. All this noise is sudden changes, and I think you hopefully will see this in the on a proper oscilloscope at some point. This is a COVID situation, so you may not have seen it in the lab. But once you go to the lab, have a close look at one of these signals. You see a tiny amount of noise on top of your signal at all, for all inputs, right? And those noises, those are spikes. You're taking, if you pass this through a differentiating circuit, it differentiates spike. So you get even larger spikes. What happens, what that means is that it amplifies the noise for you. So the other way of thinking about it is that those spikes represent fast changing signals. The gain of your differentiator goes up with frequency, so all those high frequency stuff are going to be amplified by your differentiator. So a differentiator in practical situations increases the noise in your signal. An integrator does the opposite, right? So the noise high frequency changes, the gain drops as you go up in frequency. And for that reason, we do not really like to use differentiators in practical situations. However, and then actually if there's a topology that gives you a differentiating behavior, you probably want to avoid that. You want to find a way to tame that circuit and make sure that the gain at high frequencies is not out of control. So that's that for the linear circuits with op-amps, with resistors and impedances. You have a bunch of suggested problems to keep you busy and make you practice some of the concepts that we talked about. The following lectures and the final lectures for this course are going to be about the non-idealities that we have. So far we assumed the op-amp was ideal and it was doing its job perfectly and faithfully according to the golden rules that we had. But practically there are some limitations, obviously, and we're going to see how the device behaves under practical situations and how we can address some of those non-ideal properties of the op-amps. So that's that, and I'll see you at the next lecture. Thank you.